Good morning to all. Myself, Dr.P. Gopinath, Assistant Professor, Selection Grade, KIT, Kalaignar Karunanidhi Institute of Technology, Coimbatore. Today we are going to discuss the subject is B23 BTD 301 Signal Processing. In this course, especially for second year VLSI, VLSI Design and Technology specialization. In this topic, that is a Fourier Transform. So in this unit that already we have discussed, that is a unit 1 is a classification of signals and system. Then according with we have further classified continuous time signal and a discrete time signal. So that is a unit 2 title is continuous time signal analysis. So in this continuous time we are going to perform Fourier series and transforms and Laplace transforms. So today we are going to discuss Fourier transform. Fourier transform and its applications. So what is meant by signal? Signal, it is a physical quantity carrying some information and it varies with time. So generally signal is classified two types: continuous time signal and a discrete time signal. Then here system, what is meant by system? System is a output, that is a feedback system is there, that is output is purely depends on the input. So these are the part, that is a signals and system we are going to analyze using some mathematical tools. So in this tool mainly that is a Fourier should be derived, that is a Fourier transform. So Fourier transform especially we are utilizing, that is a periodic, we have generally classified periodic signal and non-periodic signal. So periodic signal only apply for Fourier series. Then periodic and non-periodic, both type of signals we are using Fourier transform and Laplace transform. In these transforms especially we are using different applications like fiber optics, then signal processing, then medical applications, then speech processing, image processing, then finance level of analysis. So these are the applications we are utilizing this type of transforms. Then when to use Fourier transform? So here generally we are classified two part, that is we know that aperiodic and periodic, then continuous and discrete. So in this part we are analyzing, that is a continuous Fourier transform, continuous signals. So that is our unit 2 is classified, that is a continuous time signal. So continuous Fourier transform we are going to discuss. So let's start with, that is a classification of periodic phenomenon. So you can see the example, that is a periodicity in time. That is a phenomenon comes to you. You can see the use frequency. In this example, that is a continuity is there. Then fix the position of object. Then periodicity in space. That is a time and space is main constraint. That is use period. Fix the time and measure how the pattern is distributed in space. In 1807, periodic signal could be represented by sinusoidal series. Why sinusoidal? That is, they are orthogonal. So these are the basic characteristics of sinusoidal signal. The shape of signal will not vary. When used in LTI system, linear time invariant system, they are smooth and has finite power, then violates none of our criteria for real world applications. Then you can see the periodic and aperiodic difference. This periodic, in this waveform illustrate periodic signal. A signal that repeats its pattern over a period. It can be represented by mathematical equation. In this classification, deterministic signals are always periodic. That is a power signals. Example, that is a pendulum activity. You know the example. Then aperiodic signal, that is a random signal. Generally, we have call it as aperiodic signal. This signal does not repeat its pattern over a period. Then it cannot be represented by a mathematical equation. So this type of signal is called aperiodic. That is a example chotic signal, then ECG signal. So these are the signal is real-time examples of aperiodic. Then why can't we use Fourier series for aperiodic signal? So that is the first question, right? So in this Fourier series only for periodic signal. You can see, you know the formula an, that is a naught, an, bn. These are the coefficients of Fourier series, right? So here an generally we denoted 1 divided by 2 pi integral minus pi to pi f of x e power minus I n x dx. So the Fourier transform is derived from Fourier series only. That is, Fourier transform is the envelope of the Fourier series. Hence, the frequency domain becomes more finer for periodic signal. Moreover, being able to express a periodic signal as a discrete sum of frequencies is a stronger statement than expressing it as a continuous sum via the inversion formula. So, origin is Fourier series. So, Fourier series into Fourier transform. Then next one is a linear time invariant system. So linear time, that is it must be satisfied to conditions. That is a linearity. That means a superposition principle should be satisfied. Then next one is a time shifting. That is a time shifting. These are the two properties. So these two properties must satisfy. That system is called, that is a linear time invariant system. So you can see the example, that is a linearity we have analyzed here. Then time shifting waveform should be denoted. Then Fourier transform. So transformation of signal from generally time domain into frequency domain. The significations of time domain and frequency domain. So in this time domain or spectral domain representation of 1 kilohertz waveform should be illustrated here. The frequency domain representation of signal should be mentioned. So you can see the example, input signal LTI, the waveform we have denoted. So the waveform illustration should be mentioned in this plot. So origin is time domain. So in this periodic and sine wave mentioned, that is a time domain waveform. Then time versus amplitude. So we have extract from to obtain our frequency domain values. So we have mixed the different range of amplitude values. Then we have extracted here to obtain frequency signal. The Fourier transform procedures, that is a Fourier transform analysis, the break the signal or functions into simpler constituent parts. So this is the formula, that is a f of j omega for the limit value of integral minus infinity to plus infinity f of t e power minus j omega t dt. That is analysis equation. Then Fourier transform synthesis, that is a resemble of signal from its constituent parts. So this is the formula for synthesis equation. F of t equal to 1 divided by 2 pi integral minus infinity to infinity f of j omega, capital F of j omega e power j omega t d omega. So both operations, that is analysis and synthesis, accomplished by linear operation. So here the continuous time Fourier transform. In this continuous Fourier transform, we are obtaining that is a f of j omega. So in this part, we have additionally we have calculate magnitude and phase angle. So magnitude, that is a determine the contribution of each component. Then phase, that is a determine which component we are utilizing. So every Fourier transform, we obtain that is a time domain into frequency domain. After that, we have calculate magnitude and phase angle. So this is the formula for a discrete time Fourier transform. The representation should be illustrated. That is a f of omega summation n equal to minus infinity to plus infinity. That is a f of n e power minus j omega n. So this is the formula. So equivalently we have obtained that is a magnitude and phase angle. That is a magnitude equation f of j omega. Then e power j, that is a phi of omega. That is a phase angle illustration. Then here important condition should be derived. That is a Dirichlet is a mathematician, should be denoted. That is a condition for existence of Fourier transform. That is a Fourier transform having first one is a finite number of maxima and minima over any finite interval. Then finite number of discontinuities over any finite interval. So here we have a maximum limit is a minus infinity to plus infinity. Then here the maxima and minima value is a finite number. Then next one is a finite number of discontinuities over any finite interval. The next one, that is a third condition, is absolutely integrable. That means energy of the signal, that is a mostly that is a finite. That is a equation in mentioned, that is a infinity to in, that is a minus infinity to plus infinity modulus of x of t dt, that is a less than infinity. That is a case we have mentioned, that is absolutely integrable. So these are the three cases derived from Fourier transform. This is the condition of Dirichlet condition. So Fourier transform having lot of property, that is a more than 10 properties are having. So in these properties illustrated how to perform this type of transforms. So especially linearity, time shifting, frequency shifting, time reversal, time scaling, differentiation, convolution. So these are the property, that is especially we are using Fourier transform. So these are the property should perform what type of operation we are going to do. So mainly we have calculating, that is a linearity, differentiation, convolution, Parseval's theorem. So these are the important properties of continuous time signals. Okay, okay, thank you.